Okay, so welcome back. Next up, all right, we're going to take a look at something a little bit different. Okay, we're going to take a break from equations and derivatives and actual calculations and evaluating. We're going to take a look at graphs and determining whether at any given point if the function is differentiable or not. Okay, so first of all, let's just always remind ourselves that when you are getting the derivative, you're getting the slope of the tangent line. Okay, so at some places on a graph, you cannot calculate the slope of a tangent line for different reasons. So we're going to get into that, but at first, okay, let's just do a quick review of continuity. So if you remember in the limits unit in pre-calculus 12b, we took a look at doing proofs, proving if a function was continuous or not continuous at any given point. And that definition is up above here on this slide. You can see that it has to meet the three requirements. The point has to exist. The limit as x approaches that value has to exist. And both of those values have to be equal to one another. Okay, so we're not really doing a whole lot of continuity, but you have to know that a function is continuous in order to get the derivative. Okay, so and again, the informal definition of continuity is that if you were drawing a function by hand and you had to lift your pencil off the page and put it back down somewhere else, then it is not continuous. So things like vertical asymptotes would interrupt a graph, points of discontinuity, PODs, holes in the graph, a jump in the graph, those types of things would result in a graph not being continuous. The focus in this unit here is on whether a function is differentiable at a given point or not. So in order for a function to have a derivative at a particular x value, all these conditions have to be satisfied. So first of all, the function has to be continuous. So if there is a break in the graph in any kind of way, a POD, a VA, any of those things, okay, then at that particular x value, the function is not differentiable. Also, in addition to that, okay, the graph at that particular x value has to be smooth. And what we mean by smooth is there can't be any sharp corners or cusps. Okay, so a graph has to be like a smooth graph and without any sharp corners. If there is a sharp corner, then it is not differentiable at that particular x value. And then as well, this one is very less common. It happens very rarely. But if you have what is known as a vertical tangent at that particular value of x, then the function is not differentiable there as well. And we're going to all see this with one particular example. Okay, so on this next slide, what I have is I have a random graph drawn. I don't know what the equation for this is, but as you can see, this is a graph that is broken up into several different pieces, and the function is differentiable at certain places, but not everywhere. So first of all, okay, what I've done here is I've identified 6 different x values, a through f, and in most of those cases, the function is not differentiable. So what I have below is whether at each of those 6 different values of x, whether the function, the derivative exists or whether it does not exist, and the reasoning behind that. So as we move from left to right, okay, you can see at A there's a jump in the graph. Okay, at A it is discontinuous. All right, we move up and then we have to drop down to continue the graph. So the graph is discontinuous at A. That is called jump discontinuity. So we would say that the derivative at that particular value does not exist. So notice that I have f prime of x drawn in here. I should probably do something like this instead. I should probably say f prime of a does not exist, because the derivative does exist to the left of a. Okay, the graph is smooth and continuous there. And to the right of a, you can also get the derivatives, but you can't get the slope of a tangent line at a. For example, does the slope look like this? Is that the tangent line? Is this the tangent line? Is this the tangent line? Is that the tangent line? We don't really know, okay, because the graph is not smooth, because it has a corner in it, or sorry, it has a discontinuity. We really don't have any kind of way of knowing what the tangent line is. So it's discontinuous at A, discontinuous at B because the point doesn't exist at all. All right, that is a POD, a point of discontinuity, and a graph has to be continuous to have a derivative. And then at C, this is the rare case that I was referring to. Okay, at C, we have what is known as a vertical tangent. Okay, the tangent does exist, but it is a vertical line. Maybe I didn't draw this completely correct, but the tangent line is vertical, and the slope of a vertical line is undefined. Okay, so because you can't do a slope of a vertical line, because when you do a vertical line, you don't have a run. You have a rise, but you don't have a run. So basically, if you did a slope of a vertical line, you would have whatever the rise happens to be over the run, which is 0, and you can't divide by 0. So long story short is that if your tangent is completely vertical, which rarely ever happens, then the function is not derivative or differentiable at that particular point. And then once again, at x is equal to d, we have a vertical asymptote. And of course, the graph is discontinuous whenever there is a vertical asymptote. So I can't get the slope of a tangent line at D because there is no point there. At E, there is a tangent line. Okay, at E, whatever this value is right here, okay, we know that at this particular point, it is continuous, it is smooth, and it's not a vertical tangent. We don't know exactly from this diagram without an equation what the tangent line is, but we know it's going to go something like this right here. There's definitely a tangent line. So in this particular case, okay, we would say for this one right here that at f prime, and once again, I should probably change these, okay, because I want to be more specific. At f prime of e, the function exists, the derivative exists. Okay, we have a tangent line at that particular point. But then again, at f, okay, we have what is known as a sharp corner or a cusp, and here we cannot get the derivative. Okay, it is continuous, but because it's not a smooth curve, it's a sharp corner, we cannot get the slope of the tangent line, so we cannot get the derivative. And the reason why is, okay, let me try to put in a tangent line here. Well, because it's not smooth, I don't really know if it goes like that. If it goes like this, could go like this here, could be any number of tangent lines. When you have a sharp corner, it's not clear what the tangent line can be. So in this case here, it is a sharp corner or cusp, which is one of the 3 ways a function is not differentiable.